So I'd like to welcome everyone to the first session of the last day of the workshop. Thank you all for attending. Today's workshop sessions for the day are around mathematical physics. And it is a great pleasure to have our first speaker be Charlie Bennett, who will be bringing up his charts in just a bit. Charlie, go ahead. Let me give you the presenter.
Okay.
You now are presenting, so you can bring up your charts.
Okay, I'm going to share my screen.
And Charlie Bennett will be talking to us about Brownian molecular computing.
I'll switch to my screens here. I'm going to do one. I have to find this thing here. There we go, sharing the screen. Let's see. And I want to start this as a now I have to get it going so that it's full screen.
Yep.
There we go. Okay, so I'm going to be talking about the thermodynamics of computing and the thermodynamics of fault tolerance. Now I have to get, okay, so the thermodynamics of computing, where that has to do the question of reversibility, is a manifestation of the second law, which is famous for having a lot of different manifestations in the world, things that seem to have nothing to do with each other. There's the, I think I started talking about this yesterday, or 2 days ago, but it's just reviewing, these are some of the famous statements and consequences of the second law, including ice skating. But the best statement in the context of information processing is the one that was Landauer's principle, as later enunciated by Ben Schumacher, which is that no physical process has as its sole result the erasure of information. And this is just a consequence of reversibility of physical dynamics, either classical or quantum under unitary evolution. Now, people who are new to the field or are approaching entropy from one direction or another are often puzzled by the very different sounding definitions of entropy that sound like they're talking about completely different things. This thermodynamic entropy, which was a state function that you could, it had an arbitrary additive constant, and you could track changes in it by following the heat flow over into or out of a system over a reversible path and just dividing it by the temperature. Oh, then there's the statistical entropy, which is the one that Shannon used, and it turned out to be very much the microscopic equivalent to the thermodynamics of Carnot and Clausius and Kelvin. And then finally, there's the algorithmic entropy or Kolmogorov complexity, which was introduced in the middle of the 20th century, and it looks like it's not about physics at all, but it actually is a function of statistics, as a principle we also saw yesterday, is that if any ensemble or any distribution is concisely describable, then its statistical entropy is very nearly equal to the average of its algorithmic entropy of its members, or indeed its concentration of measure says that it's nearly equal to the algorithmic entropy of almost every one of its members. Okay, so let's apply these things to the thermodynamics of computation. And there are two principles there. In the ideal case, which is the way people usually think about thermodynamics, and when they do these thought experiments with frictionless pistons and processes carried out at in the limit of zero speed to get the process reversible. So in the case of computing, it says that that there's no way to erase information and reversibly, and that if you make a computer reversible so it doesn't have to throw away information, it can operate with arbitrarily little entropy production per computational step. Well, of course, the computers that we use all the time aren't like that. They're irreversible. But let's go to the reversible models of computing. And there are basically two kinds of those. One was the dynamically reversible computing, which is the best example of that is the Fredkin's billiard ball computer. So with ideal classical billiard balls, you can use them to do logic. And so this means these elastic collisions of billiard balls together with, I guess you need some barriers or mirrors for them to bounce off, can do any computation. And then the other one, which I explored and Landauer began exploring, is the Brownian computers, where the ideal is not to follow it, have a trajectory do the computation, which is obviously very unstable with respect to perturbations by coupling it to an environment, or even an error in the initial conditions. This is a chaotic system, that billiard ball computer. But the idea is that we don't try to constrain the velocity at all. We let everything do a random walk, jiggling around in the low energy labyrinth of accessible configurations of a configuration space of some system whose potential energy function is designed to make the computation the low energy part of the configuration space isomorphic to the computation. And that's the way biological processes such as RNA polymerase work. And I'm going to show you a little bit about that soon. But to give you a feeling of what it's like to be in one of these biological systems where things have a definite shape, but everything is jiggling around all the time, but not jiggling around enough so that it falls apart and loses its structure. Here is one of the most important biological structures, which is a lipid bilayer, or it's a molecular dynamics model of one. And it shows how it can retain its shape because it is lower energy than if it fell apart and all those lipid molecules in the middle dissolved in the water on the edges. So here it looks at that. It just goes like that for a long time. And so it keeps its shape, but no part of it has any, in fact, at any time, each atom there will have a Maxwellian distribution of velocities. So how do we use that, or how does nature use that to do computations? Well, a very simple computation is tape copying, and this is done by an enzyme called RNA polymerase, which copies a DNA original onto an RNA copy here, and it uses these monomers like guanosine triphosphate, which reacts here, and because the guanosine can make a base pair with the cytosine, it gets put in and the pyrophosphate gets released, and then it continues on, and so it becomes a one-dimensional random walk along a washboard potential, and the driving force is just determined by the ratio of concentrations of these pyrophosphate molecule with the triphosphate molecules. And that means if you tilt it the other way, it can uncompute, it can undo the computation that it just did. So this is a reversible computation, and if there was never any error, you could compute with arbitrarily little, you could copy with arbitrarily little dissipation in the limit of zero speed. And that's in accord with Landauer's principle because it is a logically reversible process. Now, unfortunately, or it should never say anything which is true, is unfortunate, I guess. These DNA and RNA bases don't behave absolutely perfectly. There is not a, for example, adenine, sometimes a hydrogen departs from the amino group at the top and attaches it onto the ring. And that means for a while it behaves like guanine and makes a bad base pair. So the RNA copying is not perfect. It's around 10 to the minus fourth or so per RNA base copied, which is okay in protein synthesis because you get maybe a few wrong amino acids, but most of the time the protein is manufactured correctly. But it's not good enough for DNA. So in order to get DNA copied properly, you need a better copying mechanism, which involves proofreading, which I'll get to later. But for the moment, I'll stick to this simple case of the reversible tape copying with errors. And so here's the kind of potential energy landscape. We'll have an initial state, an intended successor of that state, and also maybe an intended predecessor, which are connected by low energy barriers. But then there's a higher energy barrier in order to get to the error state. So error correction is many to one, so it has a thermodynamic cost. If you don't try to correct the errors, you'll get them. And in fact, unless obviously, the system's desire to make errors itself is a thermodynamic driving force, which you can be harnessed to reduce the work of error correction, and we'll get to that later. So looking at this tape copying process, we see that as we go from one number of units of base copied onto one more, there is a driving force, there's an activation barrier to be overcome to do the correct step and go forward and backward along that. That's the driving force. But there's a higher barrier for putting in the wrong base. And that also means there's a higher barrier for taking out the wrong base. So these copying errors act as reversible obstructions, difficult to insert and difficult to remove. And that means we can think about the process of copying with errors as a walk, and I'm going to use, because instead of 4 bases, I just use 2, because the general principle of making errors is the same whether we have 4 bases or 2. So we have a correct sequence and an error sequence. And the idea is every step along this tree is inserting a correct base, another correct base, a third correct base, and in each of these steps you can make an error. So we've got a binary tree, but with different numbers of errors as we go down here. But all of these states are energetically degenerate. The only place where the error costs anything is when the template and the copy strand are base paired with each other, which is they're not at the beginning and end of the process. And because of that, the fact that errors, that there's a certain desire of the system to make errors. In fact, as you vary the driving force, you get something quite different from what it would be in the ideal one-dimensional random walk. In the one-dimensional random walk without errors, if you have a positive driving force, it goes forward with a dissipation and a speed proportional to the driving force. If you make a negative driving force, it goes backwards with a dissipation and speed proportional to the driving force. But here, what we have is an intermediate zone where it actually goes backward while charging up the battery, because it's making so many errors by going backward and creating garbage that you can harness that to charge the battery up. So we have an uncopying regime which doesn't begin until the driving force is negative. That is, it's charging up the battery, and then between 1/3 and 1/2, you have a paradoxical regime where the copying goes forward, driven by the system's desire to make errors, even though we're trying to push it backward. And then finally, when you push it back forward far enough, the copying rate goes up and the error probability goes down. And of course, the dissipation goes up. So getting back to DNA replication, you need to have something that's much more reliable than that. And that's done by this mechanism that was introduced by Hopfield and Ninio, which is called kinetic proofreading. And it is equivalent to introducing another enzyme or another active site on the same enzyme, where, and as I showed in this case, this is like the RNA polymerase. This set of reactions where the purpose of the reaction is to introduce a new base to the sequence of the, this is the first reaction, and excuse me, I don't mean the left column, I mean the top part of the thing is what I showed. So this is the ideal thing. It's trying to introduce the guanine, but in fact, sometimes because the adenine looks like a guanine, it occasionally introduces an adenine here. And if you didn't do anything more about that, that would leave about 10 to the minus fourth of the time errors. But what occurs is that there is another reaction which uses different reactants and has different products, which is a digestive reaction, a hydrolytic reaction, and its goal is to take out bad bases. And so, like a proofreader, the copyist has a large probability of putting a correct letter in and a small probability of putting a wrong letter in, but the proofreader doesn't try to put errors in, put letters in. It has a large probability of taking out good letters, bad letters, and a small probability of taking out good letters. And it can do that. These reactions can be driven in opposite directions because they have different reactants and products. And so when you adjust the reaction rates of these things optimally, the product, the chance of introducing a base wrongly and not having it taken out by the hydrolytic reaction is the square of the error probability. So there's a 10 to the minus fourth selectivity for each reaction. You get a 10 to the minus eighth error probability, which is good enough for DNA replication. So that's how the problem is solved biologically. But let's go back and think about the thermodynamics some more. Oh, this is the diagram of this complicated phenomenon I was describing without the proofreading. So as I say, this is the regime where copying goes backwards. Here it goes forwards, but very slowly. It charges up the battery and makes a lot of errors in the product. That's not a very useful regime biologically. And here we drive it forward, and as we go higher driving force, we get faster copying, lower error, and more dissipation per step. So fault-tolerant computing has generally been studied in this high dissipation limit. People don't worry about the erasure cost, so they drive everything very reversibly. But as an interesting subject, at least one should understand whether this requires a lot of dissipation or you can even do it with very little dissipation. And that's a field that's explored by chemical engineers when they try to design things like a distillation column or isotope separation. I'm going to go back and talk about this. Oh, and here's the trade-off that I studied nearly 30 years ago. 30 years ago? Maybe more, 40 years ago.
41, to be precise.
Okay, so anyway, so I hadn't been aware of this paradoxical behavior, so I just did the optimization of all these reaction rates for the proofreading and non-proofreading system. And for the proofreading system, it looks nice. Like in the limit of high dissipation, I start off with a 10 to the minus fifth error probability per step. In the proofreading case, it goes up infinite dissipation. I get 1,000 KT per step. I get 10 to the minus 10th error, and then I get an error half the time if I'm not pushing it. And it goes smoothly down, just what you'd expect. But the no proofreading system did a funny thing. It had this going up and then down, and it's because that it had that paradoxical regime. And what's going on here is that it's making a lot of errors, but it's not costing as much dissipation because it's saving some of that entropy in the form of the garbage it's charging up the battery by making garbage. So it works in terms of what the job it's trying to do. It has more dissipation and less speed because it doesn't have as complicated a hardware setup. So the lesson here is by making the hardware more complicated, for example, by doing multi-stage proofreading, you might get a limit in which there was very good error correction without much irreversibility. And that's what I'd like to explore. And here's an example of one way you could do it. Here's our original tree of computation where we're driving it forward. And so the forward reaction is more than the reverse reaction, but it also makes some of these errors. But the errors are hard to take out once you put them in. So in order to get them out, we add this extra reaction, which is undoing the forward steps, but undoing it in the direction of trying to take out the bad things instead of trying to put in the good things. And so for each of those things, you can see there's a cyclic thing where there's dissipation even at zero speed, because things just cycle like that and convert the free energy into heat. But the consequence of this is that it behaves, instead of like an energetically indifferent but kinetically selected specificity, is one where it looks like it emulates a system in which the errors have a permanent energy cost even after incorporation, but at the price of continual dissipation. So if you would do multi-stage version of this, and I haven't explored this in general, but it looks like we can get in other words, we have a provisional acceptance before we actually we have a writer and a proofreader, and then a second stage writer and a second stage proofreader. You could do n stages of writing and proofreading, and we get the same kind of binary tree, which can be analyzed. So I suspect that this will turn into simultaneously low error, and maybe even arbitrarily low error and low dissipation in the large n limit, where n is the number of stages. But I don't know. Should be looked at. And what about more general computations than copying? This is why I think chemical engineers might know the answer to the question. But let's take this old idea from Darwin and Spencer that the origin of life and perhaps of all kinds of complexity comes from dissipation. You take a system that's sufficiently rich and you give it some free energy source, and if you leave it long enough, it's going to do interesting things, like, if nothing else, interesting convection currents. But if we put the temperature difference on a tank of water in the wrong direction, it doesn't do anything except have a static heat flow. It's sort of a trivial analog solution of the Laplace equation. But what if we turn of course, if you turn the temperature gradient upside down, you get some interesting stuff. But I'm going to say just put some impurities in the water and wait a long time in a very large tank of water, and then the impurities will self-organize into a civilization which includes people and trees and light bulbs and turbines to generate electricity from the temperature difference. And if you have a big enough tank and a competent enough civilization, the people can repair the turbines faster than they break down, and so the civilization can colonize the whole infinite tank. So this is a reason why the thermodynamics of weakly dissipative computation, or computation in weakly dissipative environments, is an exciting topic for research. And that's the end of my talk.
Thank you very much, Charlie. That's great. I guess we could move on to the next speaker, or we could ask Charlie questions if there are a couple of questions. We have a few minutes.
Hey, Charlie, this is Yuhai.
Yeah, I knew you'd have a question, yes.
Yeah, I actually have many questions, but anyway, let's start with this magic corner that you said. You said that you might expect to have low error and also low energy dissipation rate. If you can put up that chart again. And my question is that is that the region, the sort of adiabatic region the performance on the error and energy costs are good, but the speed is terrible. I mean,
yeah.
So is that? I mean, I couldn't make out quite right what.
Oh yeah. Let's go back to that. This is
next one. Yeah, next.
There. This one here, right? Or
next one. Next slide. I think you said that it probably was more study. Further down.
Oh, it's the one with the multi-stage proof.
Yeah, multi-stage. Yeah. Right.
Yeah.
So does that mean? I mean, this seems like. I mean, people have thought about multi-stage proofreading in the context of, let's say, immune system, because basically that it takes not just one step. So they actually can improve the error by whatever number of stages of proofreading by the power of number of stages. Like say,
That's right.
electric
Yeah.
proofreading of Hopfield is raised to the second power because you do one step, one reversal reaction. But if you do multiple steps, you could imagine that it's raised to the nth power, n being the number of stages. So,
Yeah, and so this here shows the two-stage or the
Right,
proofreading of Hopfield.
but in that case, we also know in those multi-stage proofreading case, the energy card is also n times of whatever one stage proofreading that would cost you. So that seems to be not quite what you have there.
That's right, because and the reason is because these are biologists trying to solve this problem, not chemical engineers. The biologists say our high energy phosphate, which we use each time, has a certain free energy, and it's pretty much irreversible. It's enough so that it makes the thing happen. Right. So what we're worrying about is what's the error probability due to the imperfect recognition, and how many stages of ATP do we have to throw at it to get it down? Right. And it goes as the power, as you said. Yeah. But what I'm saying is if you were trying to optimize the whole system, you would vary the chemical potential of your triphosphate or ATP because you wouldn't want to dissipate any more than you had to. And maybe you'd want to do, instead of 3 very strongly driven steps, you might want to use 10 weakly driven steps. And that's exactly what people do in these isotope cascades. They have a terrible selectivity between U-235 and U-238, but they use thousands and thousands of steps.
I see. So you think it's because of the quantization of energy unit in biology, ATP, basically, hydrolysis of ATP?
No, there are things that biology could have found, things that are more dissipative, or take the pyrophosphate, which is equivalent to 2 ATPs. Right. But it's just that the biologists think we've got a certain, they think the way computer engineers think, and the way that people are doing fault tolerance. They're not trying to do the thermodynamics of this thing in full generality. They're trying to take the equipment that they have and get the dissipation. What they mainly want is good selectivity, and they're trying to do it with not too much dissipation.
No. Let me try to be precise with the language. Yeah. They don't think, they know that there's only your only currency of energy is ATP, and you don't have any smaller unit. If you want to use, if it's enough to use 1/10 of ATP, I don't think there's a molecule that have 1/10 of ATP.
No, but there is. Here's a biological example. Consider the ribosome. There, the currency is the hydrogen ion concentration inside and outside, and it's not
continuous.
Ribosome. Okay. I mean mitochondrion. Right. Mitochondrion. Right. There, it's continuous. Right. So if you that's an example where it really works well. I mean, we wouldn't be alive here if we didn't have mitochondria doing this, using this continuous. So it's not that it's inherently absent. It's just that, like trying to make fault-tolerant computer work in the realm of high error, which is what they have to do in isotope separation and what they have to do in building a quantum computer, the first thing is to get it to work, and then the next thing is to get it to work optimally.
Okay, let's talk offline. I think
no. What I suggest is we can continue this discussion in the discussion period and panel session. I think